Next, we're going to look at different ways of arranging multiple resistors in a circuit. If you have more than one resistor, there's two different ways you can connect them. You can connect them in what's called a series circuit or what's called a parallel circuit. And we'll finish off by looking at something called electrical power. First, let's look at a series circuit. And here you can see an actual series circuit hooked up. You've got a battery, and there's the positive terminal and the negative terminal. And so you can see there's a wire coming off the positive terminal. It goes through a switch, and then there are three light bulbs connected in series with one another. That's why we call this a series circuit. Now, if you think about the current, what is it that makes this a series circuit? Is that the current can only go through the battery in one way. It can only go through the circuit in one way, and the current has to pass through every resistor. And here we can see sort of a schematic of it. We can see there's the battery, the voltage source, the switch, and then the three resistors, in this case light bulbs, that are connected together in series with one another. The key thing that makes it a series circuit is that the current has to go through all the light bulbs to get back to the battery. So here's a question for you. Here we have our checkpoint question. What happens to the current in the other lamps if one lamp in a series circuit burns out? In other words, it becomes burned out, so the current can't flow through it anymore. What happens is the current, let's say this middle one burns out, what happens is the current goes through the wire, and it'll go through this light bulb, and then it'll come here and it's burned out, so the current will stop. And so actually, because the current can't get all the way back to the battery, the current won't flow through the circuit. So the connection has to be all through a good connection, otherwise the current won't flow at all. And so if this guy burns out, none of the light bulbs will light up. This can be a problem if you have Christmas tree lights and they're connected like this. And sometimes Christmas tree lights are connected like this, all the light bulbs in series. And so what happens, if one of the light bulbs burns out, they all go out. And you don't know which is the bad bulb, so you have to check all of them. What a pain in the butt. You would not want to do it that way. Another thing that's also worth noting, if I add more and more light bulbs in line, the total resistance of the circuit gets bigger and bigger. And so that means the current would get smaller. Because remember, if we look at Ohm's law, the current is equal to the voltage divided by the resistance. If the resistance gets bigger and bigger because we're adding more light bulbs, I'm dividing by a bigger number, so the current goes down. So if I add more and more light bulbs, each bulb will be less bright than they were before. And so here I've taken this directly from your textbook. It's basically the rules that series circuit follows. And so here's some of the rules. So electric current has a single pathway through the circuit. There's only one place for the current to go. The same current has to pass through each part of the circuit. The second rule is that the current is resisted by the resistance of the first device, then the second, then the third. So the total resistance to the current is the sum of the individual resistances. And so if each of those three light bulbs had 10 ohms of resistance, the total of the three light bulbs together would be 30 ohms. The third rule is that basically Ohm's law is obeyed. And of course, we remember Ohm's law says V equals IR. But in this case, rather than using the individual resistors of each light bulb, we'd use the total resistance of the circuit. And we know for series circuit, you just add up the resistances. I'm not going to read this number 4 to you. I'm going to explain it, and then I'll let you read it, and hopefully it'll make sense. So I've drawn a picture of a little circuit here with 3 resistors that are connected in series. Can you see they're in series? If the current comes out the positive end, and by the way, the battery terminal, the longer stick is the positive terminal. So the battery would typically a current would come out of the positive terminal and go through this resistor, and then that resistor, and then finally this resistor, back to the negative terminal. Why does current flow? We know why. Do you remember? It's because the battery is a source of potential difference, The potential difference is creating an electric field down the wire, and the electric field pushes the charges through the circuit. That's the whole basis of how circuits work. Potential differences create electric fields, and electric fields push charges. So when we say there's a potential difference, we could say that this terminal could be at 10 volts and this terminal could be at 0 volts. That would mean that the battery had a 10 volt potential difference. It would be exactly the same if this guy were at 20 and that guy were at 10. It would mean there was a 10 volt difference between the terminals, and that's all that would actually matter in terms of the circuit. Now, what happens when the current goes through the resistor? Some of its energy gets used up. Maybe it's being used up to make light or heat or to run a motor or whatever it is. Some of its energy is being used up when it goes through the resistance. And remember, voltage is energy per charge. So the charges going through are the same. If the energy falls, the potential falls. And so what happens is, as the current goes through the resistor, the energy gets used up a little bit and the voltage drops. And depending on how big the resistors are, that will tell you how big the voltage drop is. How do you know? It's Ohm's law. That's what Ohm's law is actually telling you. It's telling you for a particular resistor with a current going through it. So here's R, here's I, there's a particular resistor, there's a particular current going through that resistor. V is how much the voltage drops from one side of the resistor to the other. Now, if there's only one resistor in the circuit, it's the voltage drop across the whole circuit. But if you have multiple resistors, there would be a voltage drop across this guy, and that guy. Now, if it's 10 volts here, it's going to be 10 volts all along this wire until it gets to this resistor. It would be 10 volts there, and then maybe there's, say, a 3 volt potential drop. And so here it's 7. And so it's 7, 7, 7. Maybe through this resistor, maybe the light bulb's a little different. It has a bigger resistance, and it's a 4 volt drop. So it would go from 7 to 3. And then from here, you've got to get back to 0, so it would be a 3 volt drop there. Basically, what this guy number 4 is telling you is that on each individual resistor, they'll get their own drop. And what's important to know is that all of the voltage drops across all the resistors have to add up to the voltage drop of the battery. And again, the 5th guy is telling us the voltage drop across each device is proportional to its resistance. That is, Ohm's law works across the whole circuit all at once, considering the total resistance, adding up the individual ones to get you the total one. It also works across each individual resistor. So Ohm's law works across the whole circuit and across the individual parts of the circuit. The other kind of connection you can have is a parallel circuit. And here is a battery, and the current is going down this wire, and then the wire forks. And so some of the current is going to go down this wire to this guy, some of the current's going to go through that light bulb, some of the current's going to split down here and go through this bottom light bulb here. Now you can see this switch here has been opened. This light bulb's not turned on because that switch is open, and so no current can flow through this wire. But let's say this is a 9 volt battery. We know it's 9 volts here, 9 volts here, 9 volts there, 9 volts there, 9 volts there. Then it gets to a resistor, it's going to drop. This resistor is going to drop. But there's no current, the current can't flow through this guy, so this guy just is kind of hanging out and is just 9 volts by himself. But 9 volts on this side, 0 on the other side. And so this guy's going to see current flowing through it, and this guy's going to see current flowing through it. And they're going to have the same voltage, the voltage of the battery. Here we can see this circuit here is represented in a sort of a schematic, and you can see here's the battery or the voltage source, here's the switch. And so the total current's pushed by the battery here. When it gets to point A, it splits. It can go through this top branch and this medium branch, but the bottom branch, it can't flow through because that switch is open. And so these two light bulbs will light up. Now, notice in the series case, we said that if one of the light bulbs was burnt out or the current couldn't pass through it, the entire circuit would die. You could not have any of the light bulbs light up. this is not the case for a parallel circuit. If the switch were closed but the light bulb were to burn out, it would be the same thing. And the other thing that's really cool about parallel circuits is it doesn't matter how many light bulbs you add, they all see the same potential difference. And if they have the same resistance, that means they'll all be equally bright. And so if this guy goes out, it's not going to change how bright this guy is. And if I add more and more light bulbs, it won't matter, that all the light bulbs will still be equally bright. And by the way, this is obviously the way that you want Christmas tree lights to be wired up. You want them to be wired up in parallel, because then if one of the bulbs goes out, the other light bulbs will remain lit, and you can see which one is burned out and replace just that bulb. It's much more convenient. So let's check our understanding here with our checkpoint. What happens to the current in the other lamps if one of the lamps in a parallel circuit burns out? Absolutely nothing. The voltage difference across them is the same. The current is the same. What happens to the brightness of each lamp in a parallel circuit when more lamps are added? Nothing. They stay the same. Pretty cool, right? And the last thing that we want to talk about is electrical power. Recall that regular power is work divided by time or energy divided by time. We've seen work and energy and power before. It turns out that when you apply this to electrical terms with things like current and voltage and resistance, the formula for electrical power is simply the current times the voltage. In your textbook, they actually show you how this formula is equivalent to that formula. I don't really expect you to know that, so I'm not going to show it to you. But if you're interested in, how do these work out to be the same thing, it's actually shown in your book. And of course, if you look at it and you don't understand it, shoot me a question. I'll be happy to explain it to you. I just, I'm not going to make you know it for the test, and so I'm not going to cover it in these videos. But anyway, this is how electrical power works. And by the way, do you remember what the unit for power is? It's watts. And a watt is equal to a joule divided by a second. And so energy divided by time is the unit for power, and the usual way to say it is watts. And that's true for both regular power and specifically for electrical power.